Hello everyone. In this video, I am going to discuss the physical properties of halogen compound, especially alkyl halide. So first, let us talk about the color. When alkyl halide it's pure, it show the colorless. So what is the meaning that pure alkyl halides are generally colorless. If halogen compound appears colored means it indicate the presence of impurity will be present, which means that it decomposition of the products. So if it is alkyl halides are it's appeared in the form of color means, which means that it impurities are present. And next thing is that it's a odor. And many of the volatile alkyl halides have the sweet smell, and the reason is less molar masses. So if it is molar masses are very less means the gaseous states of matter will be occurred. So volatile halogen compounds show the sweet smell, which meaning that okay, the volatile substance are with a low boiling point and relatively it's a low molar masses. So it's allow them to easily vaporized and spread into the air atmosphere. So therefore it is a volatility in nature, and the characteristic will be a sweet odor will be present. So now I just showing that flow chart of the important physical property of the alkyl halide. So what are all there it will be present. The first one is a boiling point and density and a melting point and solubility. Okay, the first thing is that here I'm showing the melting and boiling point. So organic halides are generally it's a polar nature. So why it is a nature? So did you know that the nature of the CX bond, the carbon has the less electronegative and the halogen has the more electronegative. So as a result what will happen? Partially negative charge in this carbon has the partially positive charge. So due to that it can generate the polar nature. So that is a case why it's leading to the stronger intermolecular forces, okay, in the compared to the other hydrocarbon derivatives. Okay, so in this bar diagram here I'm showing the relation between the alkyl halide and the boiling point. Okay, so in this y-axis I take the boiling point, and x-axis I just take pictorial with the uh, alkyl halides derivative. So first in this first state, in the first set I have the methyl chloride, methyl bromide, methyl iodide. So here the number of R groups are is similar, but the what about the halogen is somewhat is different. So in this boiling point will be high. So why? Here I have the methyl iodide. The methyl iodide it has the highest boiling point. So why? This is the reason why the largest atomic masses and sizes, which result in the stronger London dispersion forces are available. So that is a case why it's a boiling point increases. So as you know very well, so and if it is ethyl group, I mean the number of R groups are it's keep on increases. What? Molar masses also is increases. Obviously the boiling point also is increases. You keep in mind the number of halogen atom is increases, boiling point also it's increases. Okay, and so this is the idea about that how will be the boiling point increases from the alkyl halide. So among the alkyl halide, alkyl iodides are more boiling point. The reason is a molar masses will be higher on that. Okay, iodine it's a 1.26.9 gram per mole, and fluorine has the approximately it's a 19 molar masses. That's why. So another important thing is that it's a branches of the isomer. So what is the isomer? It's the same molecular formula and a different structure, and a different structure will be it's present. So this is known as the isomer. So now look at the boiling point value of this particular haloalkane derivative. So here I have that what is the compound name? It is a 1-bromo-butane, and this is the 2-bromo-butane. And what about this one? And this is the 2-bromo-2-methyl propane system. So now if it is number of the alkyl R groups are is increases, so I have the higher boiling point. So if it is 1 2 3 4, so now I appear the branches. So now what will happen? It's a 364 Kelvin. So now here I have the more number of branches will be present. So obviously the boiling point will be is keep on decreases. So why it is happen? More branching reduces the surface area, so which means that weakens the intermolecular forces and therefore lower the boiling point. So now in, for example, in the test tube, in the particular test tube, I have the a similar kind of molecule will be present. Okay, for example, in the test tube I take the 1 bromo butane. Okay, same compound will be appeared in the test tube. So between among them, among with that, what will happen? There will be a formation of magnitude of interaction will be present. It seems to be similar in the case of a branched one also. If I take the branched one in the test tube, so what will happen? What will happen? Here it will form the another interaction will be present. Okay, the intermolecular the magnitude of the interaction will be somewhat less comparison of this one. So now what will happen? If you want to break this interaction, I need to supply huge amount of energy. So similarly, if I want to break this interaction, a less magnitude of the interaction, I just apply the very less amount of the energy. So now if it is branches of the isomer is keep on increases boiling point also it is a decreases. If it is a longest hydrocarbon derivative means boiling point increases. And next important thing is that it's a melting point. So melting point, you just think about that, it's a nature of the solid state, it's converted into the liquid form. So especially in the haloalkane derivative. So in the haloalkane derivative, let I take the disubstituted. Okay, it's a 1 comma 2 position, it's a para. It's a 1 comma 3 position, it's a meta. It's a 1 comma 4 position, therefore it is a para. So ortho, meta, para position I have. So in that ortho position I have the 256 and 249, and para position I have the 323. So what is the meaning that the melting point depends the larger the largely on the molecular symmetry and the crystal packing in the lattice system. So if you want to generate the giant molecule of the inorganic compound, or can be organic molecule means, okay, definitely we will look up, we think about the crystal lattice. If it is crystal lattice, packing efficiency or more on that mean more melting point will be present. So why? Due to the reason of what? It's a symmetrical molecule. So due to the symmetrical nature, the crystal packing will be more efficiently packed. So if we want to better to destroy that, we need to apply more amount of energy onto that. So ortho and meta isomer are the less isomerical. So generally have the low melting point. So suppose here I have the center of symmetry of this ortho derivatives. So this is the center of the derivatives. Okay, so what about that? Here I center of rotation. So this is the center of the rotation. So among that, if I am rotate the 180 degree rotations, okay, similar possibility I am going to get that. So what about that para position? In the para position, this is the one of the possibility to can be rotate. So this is the one of the possibility. So this is the one of the possibility. Number one, if I am rotate the 180 degree, I get the similar structure. So this is the another possibility. If I am rotate the 180 degree, I get the similar structure. So similarly, in this axis, I can rotate 180 degree rotations. I get the similar two structures. So now, so this is the isomer have the more number of symmetrical will be present. So if it is more number of symmetrical will be present means more crystal lattice packing will be present. Therefore, high melting point will be present. So what about the next thing is that it is a density. So what is the density formula? Density is equal to mass by volume. So what is the meaning that? Here in this equation I can able to derive that density directly proportional to mass, and density also density it is inversely proportional to the volume. So what is the meaning that if it is molar masses of the haloalkane is increases, obviously the density also is increases. So in this derivative here I have the one chloropropane, one bromopropane, and this is a one iodopropane system. So now what about the density? Density it's keep on increases. The reason why the atomic masses of the halogen atom it's keep on increases, therefore the density is increases. So now in this particular compound, okay, here I have the more number of atomic weight of halogen derivative will be present, so therefore it is a higher uh, boiling point will be present. Density also is present. So let's talk about that solubility nature. So actually what is the meaning of solubility? It's ability of the dissolving particles of the solid into the overly dispersed in the solvent medium. So now haloalkanes are very slightly soluble in the water molecule. Okay, in the solubility nature, the vital role, it is a hydrogen bonding. It is a hydrogen bonding. So what is a hydrogen bonding? So hydrogen bonding, it's nothing but hydration enthalpy. If it is hydration enthalpy more on that, it's soluble in the aqueous medium. If it is lattice enthalpy more on that, if it, okay, what is the meaning that the lattice enthalpy more means it is a insoluble in water. Keep in mind if it is a hydration, okay, we already discussed in the thermodynamics grade 11 chapter, we already discussed that hydration enthalpy is increases means solubility also, it's soluble in the water medium. So if it is lattice enthalpy is increases mean it is a insoluble in the water medium. So now let's see that the new force of the attraction between the haloalkane and the water, it's a weaker than and haloalkane and halorine and water force of attractions. So now due to the nature of the CX1, okay, partially positive charge, partially negative charge, so therefore what will happen, it can separate into the two ionic form, okay, in presence of what we are adding the water solvent. So as a result it can ability to dissolve it. So now here I'm showing the some practice question. Arrange the increasing order of the boiling point. So first case I have the methyl bromide and this is the bromo form, 3 number of bromine will be present. Here I have the methyl chloride and this is the vicinal dihalides of bromine system. So 1,2 dibromo ethane system I have. So which one is the highest boiling point here? So here I have the 3 number of bromine will be present. Obviously this is the more boiling point will be present. So what is the next thing is that the next thing is that I have the bromine. Okay, bromine, it's a 2 number of system, therefore CH2 Br will be present. And what about the next least one category? The least one is a methyl bromide and very least boiling point will be a methyl chloride. So why it's a methyl chloride? Comparison of the bromine, all the bromine, okay, here I have the bromine system, okay, all the bromine, chlorines are its less atomic mass, therefore it is a least boiling point system. So now and second case here I have the what is the derivative? Here I have the derivative of the alkyl halide derivative of the 1 chloropropane and this is a 2 chloropropane and here I have the 1 chlorobutane system. So now if it is the number of R groups are increases, more boiling point will be present. Okay, so as a result, which is the boiling point? So this would be the more boiling point and this is the shortest hydrocarbon derivative. So this is the very least one and comparison of this particular derivative, I mean 2 chloropropane, it's a very least boiling point. Why? The branches also increases. Okay, so this is the idea about the physical properties of the haloalkane system. Thanks for